Now that we've done series circuits, here we're going to take a look at parallel circuits and some of the differences in the rules associated with each type. So here's the rules for parallel circuits. Before we said with series that the current was the same across each resistor. For parallel circuits, it's the potential difference, i.e. the voltage is the same across each resistor in parallel. So the voltage is the same everywhere. So the effect then is where with series, where we had to add up the voltage to find the total voltage, here we add up the current. So voltage is the same everywhere in parallel. The current, you can add it up across the current across each resistor in order to find the current across the battery. Okay, the equivalent resistance is also different. So with series, as you added resistors, that just increased the resistance of the whole circuit. Now think about this for parallel. You know that there's branches in the circuit, so the current essentially has choice, right, of where to go. So as you add more branches, you add more choices, and therefore you have less total resistance. So this is kind of how this works. There's a derivation. I guess we don't really need to go into that very much. It's just that if you look at the equation for the resistance, that it's actually the inverse of each resistor added together equals the inverse of the equivalent resistance for the circuit. So the equivalent resistance for the whole circuit is actually less than the smallest resistor. So that's kind of a cool effect for parallel circuits. So here's an example just like we did for series that we'll do here with parallel. So here we have a 60-volt battery or power source, and then we have it drawn into parallel. So there's a branch, and then the current basically has three options of where it could flow, where each resistor has a different resistance value. So to begin with, it's usually the first thing that you can do in one of these problems is to find the equivalent resistance for the entire circuit. So since we already know all three resistors, that's pretty easy to do. We're just going to insert the values for the resistor into our equation. One thing that sometimes students forget to do is to then invert the answer. So you're solving for 1 over R, you need to invert that then to find the total resistance, and here we get 4.29 ohms. So notice that is much smaller than any of the individual resistors. Cool effect of parallel circuits. So now that we know the equivalent resistance for the entire circuit and we know the voltage, we can go ahead and use Ohm's law to find the current. So again, this is rearranged for current, but that's V equals IR, which is Ohm's law, rearranged for current, and we find the current to be 14 amps. Okay, so once we know the current there, we can go ahead and we already know if we know the voltage is 60 volts across the battery, then it's going to be 60 volts everywhere. Yep, that's the next thing I put, I couldn't remember. So if you know the 60 volts everywhere, now you can work backwards and find the current for each resistor. So you already know its resistance value for R1 and you know its voltage value. So you use V equals IR. If you haven't noticed, you use that equation a lot in this chapter. It's nice, it's simple, it's good. And you can calculate the resistance for each one. Just like with series, how you could add up the voltages to be the voltage for the battery, the same thing here, again barring rounding. If you add up all three values for current, you should get approximately 14 amps. So that's a nice way that you can double check yourself at the end to make sure you haven't made any silly arithmetic errors. So oh, I guess that's it. I thought I had power on that one. There's no power on this one. Just that, I think that's pretty straightforward. So you have a difference in the rules between series and parallel. Make sure you understand the difference when it comes to test time, and you'll have a worksheet just like you had for series on this parallel one.